Okay, and start the backup also. Okay, we are all set now. So the plan for this week is that we are going to have this single class on Monday, the first and only live session of this week, and we are going to cover thick walled pressure vessels. Now, in the previous week, we had discussed thin walled pressure vessels, and this topic of thick walled pressure vessels is certainly a generalization of that, the thin walled pressure vessels. And it is perhaps important before we delve into any of the equations and such other things to get a intuitive feel of where it is important and what extra things we need to consider and why we need to consider that. So let's do that first. So earlier, when we were talking about thin wall pressure vessels, we were basically talking about things like this. So suppose we had a cylindrical or a spherical pressure vessel. We were considering a vessel which was having its wall very thin compared to the other dimensions. For example, in the case of the cylindrical pressure vessel, that thin wall was very small with compared to the radius. Similarly, for the spherical pressure vessel, the wall was very small compared to the radius. And the formula for the stresses which we had talked about in the case of the cylindrical pressure vessel was sigma 1 is equal to PR by T and sigma 2 is equal to PR by twice T. And for the spherical pressure vessel, we just had one sigma, which was PR by T. So this was for the spherical. Now, in both these cases, you see, we had mentioned that within this wall, this is the stress distribution, or this is the stress distribution. But the key point to understand here is that within the thickness, so suppose you zoom into this thing, suppose you zoom into this thickness, then over this thickness T, these formula, they do not give us any way of representing the possible variation of the stresses within this thickness. That is important because you understand that the kind of pressure or the kind of situation or the kind of condition which the thin wall is experiencing in the inner radius is the influence of the pressure from the inside on this thing, the gauge pressure. And on the outside, you can either think of it as the zero pressure if you're considering this as the gauge pressure, or if you're considering this as the absolute pressure, you can think of this as the atmospheric pressure. So on both these sides, there is a certain difference in the conditions. And that difference in the conditions does manifest itself in a certain variation in the actual stresses. But those variations, because of the smallness of this thickness, we do not take into consideration. So we say that all throughout this thickness, the stresses are uniform like this. Now that is all fine as long as the thickness is not. But here we want to talk about thick wall pressure vessels, and it is this thick walls where the difference will lie. So over this thickness, so if this T is not much smaller than, so T, the thickness of the pressure vessel is, earlier we had said that T was much smaller than R. Now you are going to say that this is no longer true. T is no longer much smaller than R, which means that over the thickness of the pressure vessel, over this thickness, there is going to be a certain variation in the pressure. We don't know what that variation is. I am just drawing this arbitrarily, okay? So some variation in the stresses like this. We don't know. Our interest is actually to determine the distribution of the stresses. Now one may ask the question, all this is fine and it seems like a natural thing to do after considering thin wall pressure vessels, but where exactly do you even think about these kinds of thick wall pressure vessels? So can you perhaps think of yourself what kind of situations will require the consideration of such thick wall pressure vessels? Any example from day-to-day life, from engineering life, whatever you can think of.
So where we need very high strength,
Where we need very high strength.
like in industry for
So name
pressure.
something. Name something. Like a thick-walled boiler. Anything else? Any other idea?
So the filters which we use in Orbo water purifiers.
But that is not very pressurized liquid, right? I mean, it is there, but it's not like uh, actually pressurized. It's just there. You have some kind of hydrostatic pressure there.
Sir, gas tanks.
Sorry?
Gas tanks.
Gas tanks. Okay, some special kind of gas tanks may be there. Yeah.
So in the formation of petrol or oil.
So
use-
flask.
Flask it to a certain extent, but still it is not actually pressurized flask. Because if you just pour the liquid and tighten it, okay? There is no internal build-up of pressure.
Hello, sir.
Any other idea?
So submarines?
Submarines. Submarines are, well, you can think of it like very highly externally pressurized, especially when it goes to the high depths. The hydrostatic pressure itself is very much. So, yeah, maybe you can think of it like that. Good. Anything else?
Spacecrafts?
Yes, spacecrafts. Good. Because the internal pressure there has to be maintained at atmospheric pressure, especially if you are sending people on the spacecraft, uh, then the internal pressure has to be atmospheric pressure. Okay, but the outside pressure is almost negligible. Okay, so yes, spacecraft. Anything else? Maybe something smaller, not such large industrial kind of things.
So pen.
Sorry?
Pen.
Pen. I
Pumps?
don't know. Sorry? Pumps. Okay, pumps. What about the barrel of guns? So when you fire, not when you, when a gun is fired uh, and the bullet is released, there is an enormous amount of buildup of the explosive gases there. Okay, and this was a major cause of, when I say guns, I don't just mean those handheld guns. Okay, I also include within guns cannons. Okay, those big cannons that were used during medieval times, during battles and wars. Okay, so those cannons were firing huge shots into fortresses, and there's a nice story involving these kinds of guns and cannons during. Uh, uh, during one of the wars that the Turkish Empire fought, one of the last empires that the Turkish Empire fought. And those of you have a Netflix subscription, you can probably watch that. I forget the name of the series. So there was actually a very famous Hungarian cannon maker, and he actually built one of the biggest cannons ever to be made, and that was actually used to bring about the downfall of the Turkish Empire. But sorry, not the downfall, the start of the Turkish Empire, the fall of the Holy Roman Empire. But in one of those battles, the cannon itself blew up, and that happened because of that explosive power of the gases that was building up inside. Okay, the walls were not properly designed. Okay, at that time the technology did not exist, the mass did not exist, so they could not design it properly, and many lives were lost, not on the enemy front, but on the same front from which the cannon was fired. Anyway, So there are, in manufacturing science also, there is something called extrusion molding, which I'm sure many of you will learn later, where this is very important. So there are a lot of applications where thick wall pressure vessels are important. Now, beyond this also, there is another importance of the thick wall pressure vessel, which is something indirect. It's like this, that because of the thickness of this wall, we can no longer fall back on the elementary kind of mathematical exposition that we had talked about earlier. So the simple things that we were able to do, so simple kind of force balance, which was almost like high school level physics, we can no longer fall back on that. Rather, we have to rely on something called the mathematical theory of elasticity. And it is these theories of elasticity, which is where the real fun of mechanics of solids begins. Okay, many of us who do actual research work in mechanics of solids, this large area, we fell in love with this topic only when we started discussing the elasticity things. Not because we had to constantly find about second moment of area and centroid and whatnot. Okay, not because of that. We fell in love with the subject because of this kind of things that we had to do. And the kind of lessons that we learned whilst first studying about thick wall pressure vessels in terms of the theory of elasticity, that has actually time and again helped us in addressing problems in very many apparently disconnected situations also. For example, currently one of my primary research areas is in the modeling of lithium-ion batteries, where we have to talk about the electrode particle solid mechanics at the nanometric scale. But even there, the kind of things, the kind of equations which I and my PhD students have to solve, that has a direct connection with what you solve in the thick wall pressure vessel. So there's a lot to learn. There's a lot of fundamental things going on in this thing, and I hope you'll have as much fun learning this as I had when I was your age. So before we can actually launch into the theory behind this, behind the actual discussions that lead us to the expressions of the stresses, I have to give you a little bit of background. And that background will be the absolute core fundamentals of the theory of elasticity. So we understand that in order to address this variation along the thickness, we have to have some means of addressing what is happening on a point by point basis along this radial direction. So you want to have some way of addressing this point, some way of addressing this point, some way of addressing this point, and so on and so forth. Only then we will be able to say how the variation is taking place across these different points lying along this radial thickness. So how do we go about addressing that point-wise thing? Now, herein I want to ask a question to all the fluid mechanics, all the mechanical and manufacturing guys, because both of you are studying fluid mechanics and thermofluid science simultaneously. Have you started learning about the exact solutions of Navier-Stokes equations?
Yes, sir.
Okay. So the kind of things that you have started learning there, maybe has it been started in thermofluid science?
Sir, it is in thermofluid.
Oh, it is in thermofluid science only. Okay. So if it is done in thermofluid science, great. In fluid mechanics, if it has not yet been done, it will surely be done. Okay. This is one of the most important topics. It will never be dropped from the syllabus. So exact solutions of Navier-Stokes equation, if it has not been taught, it is coming up in the next few weeks. So the kind of things that you get to study there has a direct connection with this. Okay. So let me just tell you that maybe as part of your derivation of your Navier-Stokes equation, you have come across an equation like this. Okay, maybe you have come across an equation like this, where capital D represents the material derivative, and this is something like divergence of the stress tensor plus rho B, where this B is the body force per unit volume. Now, in some special cases, you can drop this left-hand side term. So in a Lagrangian framework, if we say that the things are not time dependent, then we can directly drop this term. In an Eulerian framework, it is a little bit more difficult than that, because this dv dt, it is basically del v del t plus v dot grad v. So it's a little bit more difficult, but in a Lagrangian framework, it's straightforward that if things are not time dependent, then the material time derivative is equal to 0. And in addition to that, if you say that the body forces are negligible, then you ultimately end up with delta dot sigma, the stress tensor, is equal to 0. And this will give you 3 equations. And the 3 equations in the Cartesian coordinate system will look like this. I'm writing sigma xy, okay, not tau xy, sigma xz, not tau xz plus, but these are the same things. So this is one equation. You will have 2 more equations like this. I don't want to go down this route. Okay, it is absolutely possible to do that. I will not go down this route. Rather, what I will do is I will take a simpler situation. I will consider a material point. Around it, I'll consider a cubic element. So let me remove this point. You understand that that point is somewhere within that cube. And now I want to depict the stresses on it. Okay, the stresses to the left plane of that point and to the right plane of that point. But in doing this, I don't want to clutter up my diagram. What I rather want to do is to consider only the stress components which are parallel to the x direction. So you understand that this is x, this is y, and this is z. Now you tell me what are the components in the x direction. One of them is surely sigma xx. What is the other two? What are the stress components along the x direction?
So sigma yz
Sigma
and
yx, sigma zx.
sigma yx
Yes.
and sigma
So,
zx.
yes. So tau yx and the tau xz. Okay. So we will depict that, but this time we will take into account the fact that this distance over here, this is actually delta x. So on the left hand side, on that side, if my stress component is depicted by sigma xx, on this right hand side, what will it be? It will be sigma xx plus del sigma xx del x delta x. You understand that what I am basically doing here is to just consider the stress component over the plane x plus delta x, and because this is like a function of x plus delta x, what I'm doing is I'm doing a Taylor expansion and considering only the first term. Okay, so this is delta x by factorial 1 del sigma xx del x. That is what I'm basically doing. Okay. On this top plane, what will be the situation? If I only consider the stress component which is along the x direction, I will get one stress component like this. And on the bottom face, I will get a stress component which is like this. So this stress component is tau yx, and this one will be tau yx plus del tau yx. What will it be? Del y or del x?
Del y.
Del y.
Del y. Very good. Because the variation of tau yx is over this height, which is, I have not depicted it, but it is delta y. Okay. So this distance is delta y. And finally, what do I have to consider on this plane? So that will be, so if you consider the backward facing thing, that is the tau zx, and on this front face, the one that I'll see will be, tell me what it is, tau zx plus del tau zx, what? Del
Z into
Sir.
delta z.
del z into delta z. All right. Now, what you do is you do a force balance kind of thing. Okay, each of these stressed components will be multiplied by the corresponding area. But we are considering a cube, so I don't have any answers because in the force balance equation, all those area terms. So ultimately, what I'm going to get is something like this: that sigma xx plus del sigma xx del x delta x minus sigma xx. You understand that this entire thing is multiplied by the area of that. Next, I have tau yx plus del tau yx del y delta y, this entire thing minus tau yx plus tau zx plus del tau zx del z delta z minus tau zx. This is equal to 0. Now I'll take this equation So what do I get from here? Del sigma xx del x plus del tau yx del y plus del tau zx del z is equal to 0. Up to this point, does anyone have any doubt? Please tell me.
Excuse me, sir.
Yes.
So I did not understand that how delta yx upon delta y is coming. So can you explain for us?
This previous page.
Yes, sir.
So this one, this thing.
Yes, sir.
So you see, I am considering on the bottom face, this is tau yx. On the top face, it is what? Tau yx, but as a function of y plus delta y. Is it not? If you consider that this bottom face,
We are considering as a function in the y, not in
yes,
x.
yes, yes.
And so that element is in between the thick wall or
Element, the actual material point is maybe in the body centered point. Okay.
okay, sir.
Equidistant from all the faces.
Okay, sir.
All right. So we have this one equation obtained from a force balance in the x direction. Similarly, if you do a force balance, let me just make this yellow. This green color is not very good for the eye. So similarly, we will obtain del tau xy del x plus del sigma yy del y plus del tau zy del z is equal to 0 from a force balance in the y direction, and finally we are going to obtain del xz del x plus del tau yz del y plus del sigma zz del z equal to 0 from a force balance in the z direction. This is the fundamental thing which I wanted to show you. Okay, these are referred to as the stress equilibrium equations. The stress equilibrium equations. Please note that this is valid only when you have a non-time dependent situation plus body forces are negligible. Now, you see, this is the fundamental thing, but we don't want to be just discussing this general theory. We want to apply this kind of a theory to the case of pressure vessels. Now, pressure vessel, let me go to the next slide. The pressure vessel situation is like this. So we have a thick wall. So this is the inner radius, the dotted line represents the inner radius. And in this kind of a situation, it is much more natural, instead of talking about the Cartesian coordinate system, that is the XYZ coordinate system, instead of that, it is much more natural if we consider this this Z, this R, and of course you understand that this is the theta, that R theta Z coordinate system. Okay, so for the pressure vessels, it is much more natural to consider this R theta Z or the cylindrical coordinate system. So naturally, the question arises that if we are obtaining by considering we are obtaining the stress equilibrium equations by considering these kinds of this XYZ system, then for the R theta Z system we should be obtaining the cylindrical counterpart of these things. And that is true. We are going to obtain the exact same stress equilibrium equations, but involving the R theta Z components. What I will do is I will only consider the stress equilibrium equation in the R direction. I'll just tell you that I'm not going to derive it because the derivation of that is little bit lengthy. I will show you a nice way of deriving it, which is slightly different from the textbook version. Okay, so let me not go into that detail right now. I'll show to you later on through your Jupyter notebook derivation how that can be done. But let us write to you what. So the stress equilibrium equation in the R direction will be del tau. Del sigma RR del R plus 1 by R del tau R theta del theta plus sigma RR minus sigma theta theta plus del tau ZR del Z equal to 0. Now, cylindrical coordinate system and spherical coordinate systems always throws up surprises. So you would not expect these kinds of stress components to appear, but they do appear. Okay, ideally you would have thought that only this one appears, this kind of thing appears, and this appears. But in addition, these also appear. So don't worry about it right now. You will see through the derivation how these appear. More important to understand is that just like you will have this stress equilibrium equation in the R direction, you're also going to have a similar equation in the theta direction like this, as well as another stress equilibrium equation in the Z direction. It is not important right now to know what those exact forms of the equations are. They are complicated equations, doesn't matter. But whatever they are, you tell me one thing. First of all, how many equations are here? There are 3 equations. How many unknowns are present here? Unknowns means how many stress components which you don't know anything about. How many of them are present here?
So 6.
Yes, there are 6 unknowns present here. The 6 unknowns that are present here are the 6 stress components. Okay. So if anyone thinks that they can solve these 3 equations, they're fooling themselves because it's just not solvable. Okay, you have 3 equations and 6 unknowns. How will you solve it? It's just no matter what mathematical tricks you pull out, you are not going to solve it. So what can we do? We have to bring in more equations. So what more equations do you know? Tell me all the equations that you know in the context that you have been learning in the context of solid mechanics. I'll give you a hint here, okay? you see there are three equations, and it is our great misfortune, okay, quote unquote misfortune, that we have ended up with the unknowns here as the stress components, which are 6 in number. But suppose by some means, by some blessing, instead of these stress components, suppose these three equations involved the displacement variables. Displacement variables means u, v, and w. Okay, suppose by some means that were possible, that instead of the stress components as the unknowns present here, you had the u, v, and w. Then the situation would have been very nice. Why? Because in that case, these three equations would still be three equations, but now the unknowns would just be 3 in number. That is the displacement variables u, v, and w. U is along the r direction, v is along the theta direction, and w is along the z direction. So 3 unknowns, 3 equations, very nice. But the sad reality is that you don't have that. It is only daydreaming that we are doing. Now the clue is that it is not just daydreaming, okay? It is a hope and expectation, and that is exactly what we are going to end up with. So how can we go from 3 equations which are involving these 6 unknown stress components to the 2 equations which involve the displacement variables? So you tell me, what equations do you know which involves the displacement variables? We have discussed this in the chapter on strain and strain transformation. So from this point, whatever I'm asking you, you already know this. You just don't know this. You can immediately answer. Keep on answering, and you will see how you actually build up your knowledge. So tell me equations which involve the displacement variables. What about the strain displacement relations? So earlier in the Cartesian coordinate system, we had obtained things like this. Epsilon xx is equal to del u del epsilon yy is equal to del v del y. So those are the strain displacement relations. Correspondingly, if you go to your tutorial sheet, the one on, I hope you can see the tutorial sheet, this course website. So if you go to this tutorial sheet number 5, can you all see this? The tutorial sheet number 5?
So are you changing your tab, sir?
Yes, I'm changing my screen.
So your voice was not that clear, sir.
It's not
There is a
coming.
lag. Yes, sir. Now this tutorial
Okay.
sheet is visible.
So I am now showing to you the question number 14, the last question in tutorial sheet number 5. Can you please confirm if it is visible to you at your end?
Yes.
Yes.
Yes, sir.
Okay. So here you see epsilon rr is equal to u del r, epsilon theta theta is equal to this form involving the u and v, and epsilon r theta is also involving this u and v. Okay. So these are the kind of relations that I am talking to you about. These were in the 2-dimensional case. In the 3-dimensional case, you will have 6 more equations like this. Okay, one for epsilon zz, another for epsilon rz, and another for epsilon theta z. So all in all, you will have 6 strain displacement relations. So let me get back to my writing app now. So what I'm going to say is that I'm not going to write any of those equations. Okay, I'm just going to take an account of the equations that are actually present. So strain displacement relations. So you'll see in a moment why I'm making such a big fuss about this number of equations and number of unknowns. So this strain displacement relations, how many of them are there? There are six equations. And how many unknowns are present here? Because you see in this strain displacement relations, the previous unknowns that were present, which were the 6 stress components, they are no longer appearing. Rather, what is appearing are new unknowns. The new unknowns are what? The 6 epsilons and the 3 displacements, 3 UVW. So total how many? 9 unknowns. So till now, how many equations do you have and how many unknowns? See, 3 equations plus 6 equations, 9 equations. How many unknowns? Here you have 6 unknowns, the 6 stress components, plus the 6 unknown strain components. So 6 plus 6 is 12, plus 3 displacement variables, 15 unknowns. Okay, so up to this stage, you have in total 9 equations and 15 unknowns. So what do you need? You need 6 more equations. So who can tell me where do I get these 6 equations?
So we use stress strain relation and eliminate
Very
6 of them.
good. So you use the generalized Hooke's law. So I'm being very specific here because within the context of your second year syllabus, the only stress strain relations that you are going to study about is this generalized Hooke's law. So how many equations are here? 6. And how many new unknowns are here? There is not a single law. You have the 6 components. Inside you have the 6 stress components. But we have already accounted for them. The 6 strain components are here. The 6 stress components are here. We don't have to add them again. So now we have 6 equations involving no more new unknowns. So earlier we had 9 equations. Now at the end of it, we have 15 equations and 15 unknowns. Great. Okay. Job is done, right? So 15 equations, 15 unknowns. So no more thing to discuss about. But it is not like that. Okay. We are certainly not going to sit around and solve this 15 equations simultaneously for this 15 unknowns. Okay. That can be done theoretically, but it is never done. And certainly in the nice situation of this pressure vessel, which is our first foray into the mathematical theory of elasticity, we do not have to do this. Okay, so things can be considerably simplified, and you will see in a moment how this can be simplified. So the next slide is extremely important from the point of view of actually understanding what is actually going on physically and geometrically in the context of the pressure vessel. The things that we are going to discuss, I'm again telling you, you already know. I will just pinpoint to you the things which are actually important. So here we go. We have this pressure vessel. This is the inner radius. This is the outer radius. This is the inner radius. So the bold lines are the outer radius. The dashed lines are the inner radius. And we have some kind of distribution of uniform pressure from the outside and some kind of pressure from the inside. So this is exactly like the thin walled pressure vessel. Outside you had atmospheric pressure and inside you had the gas pressure or the fluid pressure. Exactly the same kind of situation. Difference is that the thickness of the wall is now large. Now you tell me whether this is a case of plane strain or a plane stress or something else, probably. Think about it. What are the requirements for plane strain? For plane strain, you must have the loading taking place in such a fashion that there is no distribution of the loading along the z direction, which is very much satisfied here because the pressure is uniform along the z direction. Remember that this is the z direction. So along the z direction, there is no non-uniformity in the pressure. It is perfectly uniform along the z direction. Furthermore, another requirement of plane strain is that there should not be any component of the external force along the z direction. And that is also satisfied here directly because here the pressure is acting perfectly in the radial manner. Okay, in the radial direction it is taking place. So remember that this is our radial direction. So the pressure is perfectly along the radial direction. There is no component of the external force or pressure along the z direction. So both these conditions that are required for a situation to be plane strain, that is satisfied. Okay. The implication of that is that no matter what kind of a cross section of the pressure vessel you may consider along the z direction, all of those cross sections are going to look similar. Okay, whether you take a cross section here or a cross section here or a cross section here, as long as you are not too close to the two ends, you are perfectly safe. Okay, so all of these different cross sections, they will look similar, and that is perfectly consistent with our understanding, or with our assumption that there is no variation along the z direction. Okay, so had the situation been like that, that the cross sections at different positions along the z direction, they were different, then it would have meant that there is certainly a variation along the z direction, but we are precluding that possibility. So all of these cross sections are same. What is the meaning of this? In terms, try to think in terms of the variables u, v, and w. You see, let me write it like this: u, v, and w. In general, our u, in general, okay, in general, u will be a function of r, theta, and z. Suppose we did not know anything about the loading or the symmetry of the situation, u would be generally a function of r, theta, and z. So r, theta, and z are the independent variables. U is an unknown, it is a dependent variable. V, again, it would have been a function of r, theta, and z. W would have been a function of r, theta, and z. But now we are saying that there is no variation along the z direction. So first of all, you can say that there is no dependence on the z direction. Okay, this is the direct implication of the plane strain condition. Next, can I not say that, sorry? Did someone say something? Okay, some background noise maybe. The next thing that we are going to say is that the W itself, that is going to be identically equal to 0. So there is no variation along the Z direction, that there is no displacement along the Z direction. So W is perfectly equal to 0. Now you see, you have these two things, that U is a function of only R and theta, V is a function of only R and theta. What does that mean? Well, you see, that means that if you consider any particular cross section, that cross section will look like this. Remember that this is like an annular cylinder. This is the R direction. This is the theta direction. So whatever displacement is occurring within this plane. You can have variations, or you can have deformations taking place along the radial direction, or you can have deformations taking place along the theta direction. So these are the implications that you have only from the understanding that you have plane strain. Please understand this, okay? And remember this. From plane strain, you have only this thing, that u is a function of r and theta, v is a function of r and theta, and w is equal to 0. Next, in addition to this, we are also going to consider the fact that the loading is taking place in a perfectly axisymmetric manner. In fact, the entire situation is axisymmetric. You have the geometry also as axisymmetric. The loading also is axisymmetric. Okay, so axisymmetric, from the axisymmetry, what can you say first of all? We had discussed this previously in the context of the thin-walled pressure vessel also. Tell me, what is it? Axisymmetry, what does it imply?
Del by del theta will be 0.
Very good. This is the most general thing. Okay, del by del theta is 0. Basically the implication is that no theta dependence. No theta dependence. The moment you realize that this is an axisymmetric situation, meaning that there is no theta dependence, what can you say about the two variables u and v? You can say that u does not depend on theta. V, it does not depend on theta. So basically you are saying that U is purely a function of R and V is purely a function of R. Remember that when I'm saying this axisymmetry, I mean that only the geometrical axisymmetry. I have not yet talked about the symmetry of the loading. Now I'm going to talk about the symmetry of the loading. Okay, so axisymmetric loading. Or I shouldn't say axisymmetric loading, I should say that loading purely in the radial direction. Because that is what this pressure is implying. The pressure is purely in the radial direction. What is the implication of this? Tell me. Again, we have discussed this earlier, but you tell me in the context of this thick wall pressure vessels again. The loading is taking place purely in the radial direction. What does it imply in terms of U and V? Well, the answer is that V is going to be equal to 0. Please note again, I have talked about this earlier. If you're only talking about axisymmetry, it does not necessarily mean that V is equal to 0, because it is very much possible that you can have some kind of a shear taking place along this theta direction. If there is such a shear taking place along the theta direction, definitely you are going to end up with certain displacements along this theta direction, which is depicted by this variable V. But here we do not have any such component of the loading along the theta direction. Rather, all the loading is taking place in this kind of a radial fashion, purely radial fashion. Okay. Purely radial fashion, both from the inside as well as from the outside. So we are perfectly safe, and this V can be easily set to be equal to 0. So after all these simplifying considerations of plane strain, geometrical axisymmetry, and the loading purely in the radial direction, what we end up finally is that U is just a function of R, V is equal to 0, W is equal to 0. This is very, very important. Okay, so in many kinds of books, they miss out on discussing this fundamental thing. They discuss a lot of things about plane strain and axisymmetry, but they don't show this thing. Okay, I thought that, I mean, they of course use this correctly, but they don't tell the students that this is so. So I have told you this explicitly. Next, what I'm going to consider from now on is very standard thing. Okay, so whatever I'm going to discuss next, I could have easily put that as a tutorial problem. But anyway, let me just tell you the key steps which I'm going to do. So from plane strain, I can say that epsilon ZZ is equal to 0. Epsilon Z theta is equal to 0. Epsilon ZR is equal to 0. Note that epsilon ZR equal to 0, it immediately implies that del sigma Z, that sigma ZR is equal to twice G epsilon ZR, that is also equal to 0. What is the implication of this? You go back and look at this equation that we had obtained. I'm going to copy it. Sigma ZR or tau ZR. Okay, let me write that as tau ZR. We have found out that under the condition of plane strain, you have epsilon ZR equal to 0, so tau ZR equal to 0. So this term from the first of the stress equilibrium equations, that is 0. What about this term? This term is equal to 0 from what consideration? From the consideration of axisymmetry, because this is involving a del del theta. So what we are obtaining from here is del sigma RR del R plus sigma RR minus sigma theta theta divided by R equal to 0. This is the simplified version of the equation which will be directly useful for us for addressing the problem of the pressure vessel. And not just pressure vessel, there are many other situations, axisymmetric situations, where this equation is of fundamental importance. Time and again, you will have to keep on solving this equation. Now, we want to represent this equation not directly, we don't want to keep this in terms of the stress components, rather we want to represent this in terms of the displacement variable. So what can we do? We can use the strain displacement relations and we can use the stress strain relations. But remember that things are now considerably simplified because we have already started using the plane strain condition. We are also using the axisymmetric conditions and other things. So under plane strain, when you have epsilon zz equal to 0, from the stress strain relations, what do you have? Well, first of all, you have this equation that epsilon zz is equal to 1 by E sigma zz minus nu sigma rr plus sigma theta theta. This you know very well. Now, since we are saying that under plane strain, epsilon zz is equal to 0, this implies that sigma zz is equal to nu times sigma rr plus sigma theta theta. Fine. What this means is that if you go to the equation for the epsilon rr, that becomes slightly simpler. So originally, this is the general form. Now, sigma zz, I have just obtained that this is this form. So I'm going to substitute it here. Similarly, the epsilon sigma minus nu sigma rr plus sigma zz. So here also you have, so what I'm going to do is I'm going to substitute sigma zz is equal to E times sigma rr plus sigma theta theta into here and into here. And when I do that, what I will obtain is that from this epsilon rr, I'm going to obtain, so I'm slightly simplifying it now. So I'm skipping 2 lines of algebra here. You can do this on your own. So sigma rr minus nu sigma theta theta. This is the thing. And from the epsilon theta theta, we are going to obtain this. All right. Now, you see, this is good that we have obtained some kind of simplified relationship between the strain and the stress, but we would like to actually represent these two equations not like strain is equal to something and strain is equal to something. Rather, we want to invert this and want to obtain expressions for the sigma rr and the sigma theta theta. Okay, so from this two, we are going to obtain sigma rr. So if we just solve for sigma rr and sigma theta theta, we are just going to obtain sigma rr is equal to E by. So please note that I am not doing this in my head. I've already done this in my copy. I'm just copying from there.
Sir, in second equation in RHS, it should be sigma rr and sigma theta.
Oh, sorry, sir. This one, right? This one and this one. Sorry. This would have never happened if I had done the actual thing myself. I'm copying it now, so I'm making mistakes.
So should it be sigma theta theta minus mu sigma RR?
Yeah,
Because
everything is wrong. Everything is wrong. Good. Yeah, this should be the thing. Okay. So these are the two expressions for sigma RR and the sigma theta theta that you obtain. Now, there are a few more things which I want to discuss, but since I'm running short of time, what I will do is I will officially end the class here, but I will keep on recording the thing. Okay, I have another page of discussions to do. Another page another page in my copy, maybe 2 more slides here. So I request all of you to please go to your next class. Okay, please go to your next class. I will keep on recording and you can view it later. Okay, so everyone, please leave. And
Sir, excuse me, sir.
yeah.
Sir, can you please stop till this and record another video, or else we need to download total
yes,
video if you
sir.
want to.
Oh, okay, sure. Okay. So I'm ending this class. I will just start another class after this and record the thing. Otherwise, it's going to be a huge 200 MB or 300 MB file. All right, good idea. So everyone, please leave. Class has ended.
Thank you, sir.
Bye. Yeah, bye, and
Thank you, sir.
try to have a little fun over the week. Okay, over this break, if it is possible.
Thank you, sir.
Yes. Bye. Everyone, please leave. Go to your next class. Please.
Sir, we have no class. Actually, it is cancelled.
So this is the manufacturing guys, right?
Yes, sir.
So maybe the
So
mechanical
probably.
guys have.
Yes.
Okay. But anyway, I will end this class. If you don't have any class and you want to join, you're most welcome. Okay, but I'm ending this class.